Let's take a few minutes now and talk about arbitrage-free valuation, and in particular the arbitrage-free valuation framework. This is a short reading which ought to be a welcome relief amid long and intense readings here. So we're going to look at several different approaches to bond valuation. We're really getting ready to dive into valuation of bonds with embedded options. We're not quite going to get there in this reading, but the point we're trying to make is that in an arbitrage-free framework, we're going to have these different models that we can use to calculate, and if they're arbitrage-free, they're all going to lead us to the same place. That is, if we value an on-the-run Treasury security, we're going to get a value from our model that's going to be equal to the market price of that security. All right, so that's what we basically mean here and what we're going to demonstrate. Relatively small point. I don't want you to lose track of that. It's kind of, you can end up where you're not able to see the forest because you're so busy looking at the trees, right? So arbitrage-free valuation, all this means is that it's consistent with the market price of other securities. So we're going to plug in the cash flows from a bond. We know its market price. The model is going to spit out a model price and the market price that will be the same. Or it's going to spit out a model price that will be the same as the market price, might be a better way to say that. And we're going to have, it's also going to work for what's called the value additivity principle. So we can either strip securities or we can reconstitute securities, and we're going to get the same value. So in other words, think of us as having a 30-year Treasury. So have you ever wondered why we call the cash payments that come semi-annual or annual from a bond, we call them coupon payments? Well, it's because originally the bond had coupons on the edge, and when it was time to receive an interest payment, you would tear your coupon off and mail it to the company, and they would send you back your coupon payment, right? So, of course, we don't do that anymore, but for intuition purposes, we can think about this as being, a 1-year coupon and a 2-year coupon and a 3, and, goes all the way up to maybe a 30-year. So we're going to have a coupon for each of these cash flows. Well, if we wanted to strip a bond, we could strip off all of these cash flows and sell each coupon individually, right? So if we did that, we'd sell each of these coupons individually. What would we sell them for? Well, as it turns out, the price of each of those coupons individually would be exactly the same as the price of the bond as a whole. On the other hand, what we could do is we could go into the market and we could buy all 30 of those coupons and reconstitute the bond, okay? And we would find again that the reconstituted bond and the bond that we never messed with and the value of all the strips out there would be the same. So this doesn't allow for dominance, okay? One security can't be priced more attractively as compared to an otherwise identical security. That's arbitrage-free valuation, all right? So if we want to think of this for option-free bonds, we can discount each of the cash flows at an appropriate spot rate, and we're going to do an example in a little while where we're going to talk about spot rates versus the binomial tree. So we'll get to look at that. But first, let's talk about this binomial interest rate model. So you see this here. You also see it in the derivatives material. And it's pretty easy to deal with. The approach is simple, but it may seem a little confusing the first time you do it. So as long as you work a couple of problems with this, you're going to be fine. What this is, it's a model, okay, or a system for building interest rate trees. So we're going to have an interest rate today. That's going to be today's one-period spot rate. And we're going to get interest rates in the next period that are either going to have interest rates increase or interest rates decrease. It is binomial. Okay, so one of two things is going to happen, and one of them has to happen. All right? And unlike the binomial stock option pricing model, so we have two binomial models that work very similar to each other in terms of the way we approach the actual arithmetic of valuation, but come from very different mathematical places. So there are some differences that you have to keep track of. And one of the big ones is, or one of the ones that people forget about, is with the binomial interest rate model, it's always going to be a 50% probability of an up move and a 50% probability of a down move. That's not going to be the case with the stock option model, so make sure you make that delineation in your mind. Okay, so we're assuming equal probabilities, we're assuming, that's what the model is based on, equal probability of an up and a down move. So we're going to have a 50% chance of interest rates going up and a 50% chance of interest rates going down over this next period. And then, of course, we play the game again. So from there, we can go up or down, and from here, we can go up or down, and so forth, all right? So this is, it's based on a log normal, random walk. We have an assumption volatility that drives this. What we actually end up doing is calibrating the interest rates along this lower path. Okay, and the space between, this box and this box is deterministic. Once you know this box, you know the box above it. If you have 10 boxes stacked on top of each other, you're always going to know what the spacing is between them. And you can see the formula on the next slide. Not that you need it. Why don't you need it? It's because you don't have to be able to create the tree. Okay? With the binomial stock option model, you may have to build the tree, but with the binomial interest rate model, you do not have to build the tree. You just have to be able to use it once it's given to you. All right? So it's not as bad as it might look, and I don't want you to get bogged down with how you would build the interest rate tree, because if you do, that's just going to be something that you're learning. It's confusing you. It's detracting you from studying other things, and you're not going to be using it on the exam, so don't worry with it. It's not because I don't think it's important. It's just because the learning outcome statement tells us that we don't have to be able to use that. All right? Okay, so when we look at this, what we're going to be getting is nodal values. So those nodal values are going to be forward rates. So this is the 1-period spot rate today. Okay, so it's the forward rate, 0 periods from today. That's the same as the spot rate today. And rates can either go up to whatever this rate is and whatever this rate is. Now, be careful to understand what this rate is. If we have a cash flow that comes here at time 1, so this is time 0, this is time 1, right? If we have a cash flow at time 1, we can either discount that at, well, if we have a cash flow at time 1, we're going to discount back to time 0 at this current spot rate. So that's exactly what you would say. You have a 1-period spot rate, have a cash flow at time 1, I'm going to discount it back. So whatever the cash flow is at time 1, I'm going to discount at the spot rate today. So when I look at this rate, okay, that is the rate in the up state at time 1, well, that's going to be for discounting cash flows from time 2. Right? So from here, we would play the game again, and we would say, okay, what's the value in the upstate and downstate of the world? Find the values, get an average value, and discount it back to today. So the story here to remember is that all we're going to do is find the expected value and discount it back, one step at a time. Right? So think of it this way. If we flipped a coin, and if it's heads, I'm going to give you $10, and if it's tails, I'm going to give you $0. Okay, well, if I flip a coin, 50-50, heads, tails. If it's heads, you get $10. If it's tails, you get $0. So the expected value is $5. So we found the expected value of that bet, right? Okay, now what if we say that instead of flipping the coin today, we're going to flip the coin a year from now? Well, okay, a year from now, we're going to flip the coin. If it's heads, I'm going to give you $10. If it's tails, I'm going to give you $0. So we have an expected value that's 1 period away. Well, what's the present value of that bet? Well, the expected value 1 period from now is 5. If we discount it back at the relevant interest rate, then we're going to get $4.90-something cents. Okay, well, that would be the present value of the time of next year's expected value. That's all the binomial models do. They say, look, we're going to look into the future. We're going to find cash flows in 2 different states of the world. We're going to find the expected value, and we're going to discount back. And we're going to start at some point in the future and just work backwards through the tree. All right? So no big deal here. So if we go to the up state at time 1, then we can go to the up state at time 2, or the up down state at time 1. At time 2. If we go to the down state today over the first period, so we end up down here, well, then we can go down, down, or we can go up, down to get back into the middle. And the spread between what's here versus what's here is going to be described by this. But I don't think that that's going to be particularly important, so you're not going to be building the tree. So I want you to remember that we're going to be discounting back to this node, okay, at this interest rate, right? So we're going to find cash flows over here, and we're going to find a cash flow here, and we're going to take the average of them, right? So we're going to say, well, let's take them and add them together and divide by 2, and then we're going to discount back at this interest rate to find an equivalent cash flow here at time 1, all right? So, and this, of course, the existing spot rate, and all this says that there is a 50% chance of all of these movements. Okay, so, and I've got too much chicken scratch on here for that to make a whole lot of sense. And this is talking about how we move the interest rates up, which again is consistent with this little formula. All right, so we don't need to worry about building the tree. We need to be able to use the tree. And to use the tree, we use something called backwards induction, which means we start at the end and work backwards to today. And the reason this works is because we know the value of a bond at the end of its life, right? The value of a bond is going to be equal to its par value plus the final coupon payment. So since we know that at some point in the future, it doesn't matter what interest rates are at maturity, you're going to get a check for the principal, $100 plus the final coupon payment. Well, since we know that, well, then we can just discount back, and what we're going to see is the influence of interest rate changes as we get back to today. All right? So remember, the value at maturity is known. Okay? The value at any node is the average present value of the two possible values from next period. So if we go up and then we go up again, so this is 0 state, this is 1, and this is 2. Well, then we have two possibilities beyond that, right? So if we end up at this state of the world, the up state at time 2, well, then there's a probability, there's a payoff here. Okay, there's an expected value here. Okay, and there's an expected value here. Well, we're going to find the expected value. Well, I guess I should have called that the cash flow or whatever it is. We're going to find the expected value by saying there's a 50% probability of this, a 50% probability of this, and then we're going to discount back to time 2. All right? So the value at any node is the average present value of the two possible values in the next period, and the discount rate is the forward rate for that node, which means it's going to show up here as something like 5%, something like that. All right? So if that doesn't make sense, let's plug it in and try it. I think you'll find this is pretty straightforward. So let's look at a 7% 2-year bond, no embedded options. We'll deal with that in another reading. Use the given interest rates in the tree to find the bond values for each node. So here's what we have. They have this 7% bond, 2 years to maturity. So what's going to happen in 1 year from now? I'm going to get a coupon payment of $7. Doesn't matter if interest rates go up or down. I'm going to get $7. It's an option-free bond, so it doesn't mean there's no call options or anything like that. Okay, and then 2 periods from now, the bond's going to mature. So I'm going to get $100, plus I'm going to get the final coupon payment of $7. So if we end up at the up state at time 1, where interest rates are 8%, okay, well then what's going to happen? Well, I've got a 50% chance of coming over here. What happens there? If we go to the up state at time 2, well, I get $107. So I have $107 with a 50% chance. And then if we come to the down state here at time 2, then I have $107 with a 50% chance. So when you're 1 period away from maturity, it doesn't seem quite as sexy. But what we're going to do is we're going to take 107 plus 107, getting close to the edge there. We're going to add them together, divide by 2. That's going to give us the expected value, which is also going to be 107. And then I'm going to discount that back at 8%. And that's going to give me the value of the bond here. Right? So interest rates are 8%. Looking 1 period forward, I'm going to discount that back at 8%. If I go to the down state at time 1, okay, well, then I've got, 50% chance of 107, a 50% chance of 107. Going to find the expected value. Again, 107 in this case because of 50% probabilities. And now I'm going to discount it back at 5%, and that's going to give me the value here. Once I know the value in all the nodes at a point in time, then I can step back to an earlier node and keep working back through the tree. So the arithmetic is going to look like this. So 107 in the upstate at time 1, the upstate at time 2. The up-state at time 2, 107 in the up-down state at time 2. I'm going to divide both of those by 1.08. That's my discounting at 8% for 1 period. This is taking the expected value since I have a 50% chance of each of those. So the value of the bond in the up-state at time 1, okay, is going to be $99.07. Right? And then we're going to go through and do the same thing for the down state at time 1. So it's still 107 and 107, but now we're discounting at 5%. Okay, so discount it back, take account of the fact that it's a 50% probability. The down state at time 1 is going to be 104.35, right? Now, if you're Andy Holmes, and you're going to make the Andy Holmes mistake, you're going to say, oh, I got a 50% chance of getting 99.07 and a 50% chance of getting 104.35, and you're going to, multiply each by 0.5, add them together, and then discount them by 3% to get them back to time 0. What's the Andy Holmes mistake then? Well, it's leaving off the $7 coupon. Okay, the bond was outstanding from time 0 to time 1. You got to get a coupon payment, so it's really going to be $99.07 plus $7, and then $104 plus $7. So don't forget to add in the coupon payments. So $99.07 plus 7, so $106.07, and then $104. What is that? $111.35. Multiply them each by 0.5, divide by 1.03, and you're going to get the value of the bond today of 104.35. So looks like this. So we get this 99.07 in the upstate at time 1, 101.90, and the downstate at time 1. Add in the $7. Okay, add those together, divide by 2, divide it, and then divide all that by 1.03 to discount it back, and you get a value for the bond today of 104.35. Congratulations. You just went through your first binomial interest rate model valuation. Now, here's the thing about this. We just did all this and had all those calculations. We didn't really need to do this. Okay? So this bond doesn't have any embedded options. If you don't have any embedded options, we could have just used the spot rate. Okay, so we could have looked at the 1-year spot rate and the 2-year spot rates, and as long as we're arbitrage free, okay, so everything's arbitrage free, we're still going to get this price of 104.35. Right? So we didn't have to do this for a bond that doesn't have embedded options. Okay, but what we're doing is preparing for when we do have to use it, when we do have embedded options, and we have to allow for the fact that the exercise of those options is going to actually change the cash flows of the bond, right? So the tree should be arbitrage free, so we create the tree, okay, we calibrate it to have arbitrage free interest rates. So these are just interest rates that should generate the values for these on the run, that means the most recently issued benchmark securities in the on-the-run benchmark securities, usually Treasury securities, for each maturity class. When we use an arbitrage-free tree, we force the tree to be such that for all of the on-the-run Treasury securities, okay, we end up with a value from the model that is equal to the value, the market value of the bond. So that's what calibration is, right? We calibrate the tree to force that to be the case, and you can think Holmes model here, right? So this is what we would use the Holmes model for. Okay, so valuation using a zero or a spot or a zero coupon yield. Okay, well, if we had this, we look into the same 7% 2-year option-free bond. These are the spot rates. Okay, so we have a 3% spot rate at time 1, a 4.73% spot rate at time 2. So we have a cash flow that comes at time 1. That's the $7 coupon divided by 1.03. We have a cash flow that comes at time 2. That's the 107 the return of principal and final coupon payment. We're going to bring that back 2 periods at 7.43%. Notice that we get 104.35. So you're using the spot rate curve. You're using the binomial interest rate model. Either way, you get 104.35. Well, yeah, because that's what we force the models to do, right? They're arbitrage free. They give us the value for these on-the-run benchmark securities, right? So the valuation would be the same either way. So if you know the spot rates, okay, you don't need to use that big interest rate tree. The interest rate tree requires a lot more calibration, a lot more work, as long as you don't have to use the interest rate tree, as long as you're dealing with bonds that don't have embedded options. The spot rate curve will not work for bonds that do have embedded options for reasons that we'll talk about later. Okay? Now, we could also use pathwise valuation. So this is really mathematically identical to the binomial model. Well, I would say the binomial model is one version of pathwise valuation. But all it says is we're going to come up with some number of interest rate paths, okay, where the number is going to be based on periods. So in this case, 2 raised to the n minus 1 power. So, that's going to determine how many interest rate paths we have. And then we're going to value the bond along each path. And then the average price along each path is going to be the value of the bond. So each cash flow is discounted at the appropriate 1-period spot rate along this path that we generate. And there's a couple of ways to generate it. We'll talk about 2 of them here real quick. It differs from valuation using the spot rate curve. But the valuation in the end is going to be the same, because we're going to look at the equal weight. We're going to assign equal weight to each path, and then we're going to get an arbitrage-free value, or else the system wasn't calibrated correctly to begin with. So what we have here are 2 interest rate paths. We have a spot rate of 3%, and it can go up to 8, or a spot rate of 3%, it can go down to 5. Yes, that's still down because it's the lower rate here. So we have 2 interest rate paths. We can value the bond along each path, looking at the same bond we saw previously. And when we find the average of those, okay, what we get, lo and behold, is 104.35. Notice that we had a tree that was 3% and went up to 8% and down to 5%. So we're just doing the same thing here, but without the binomial path, or without the binomial tree. We're just calling them paths. You know, so there's not much of an iteration there, right? Okay, but this does allow us to do one other thing, and that is to think of simulation. Okay, in the case of Monte Carlo, so we're going to generate, instead of just a couple of paths, we're going to generate many interest rate paths, maybe 10,000 paths, and then we're going to do some magic with the interest rates. So we may impose upper and lower bounds that are consistent with mean reversion. But in the end, we're going to calibrate our paths to make them arbitrage free. And we're going to go through and we're going to do the valuation of a security. And it's going to be the average of the value along each path. So we can think of it as saying, well, let's take the computer, plug in a model, and we'll get an interest rate path that looks like this. So this is going to be, all these different points on the path. We'll have an interest rate. Well, we can take and say, well, okay, what are the cash flows? Let's discount them back along this path, and we're going to get, something, right? And then we do it again, get this path, and again, we get this path, and again, we get this path. Eventually, we're going to have 10,000 paths. We're going to discount the cash flows from the security back along each of those 10,000 paths, add up all those 10,000 values, and then divide by 10,000. That is the average value along the 10,000 paths. And given that this was calibrated to be arbitrage-free, okay, if it's done right, then the value is going to be, for on-the-run securities anyway, the value will be equal to the market price of the security, right, or of the on-the-run Treasury security, if that's what we're using as our benchmark, all right? So the Monte Carlo method, we use this in the curriculum to value mortgage-backed securities, although really understanding what's going on is all we have to do, because you can't estimate interest rates on 10,000 paths, right? Okay, not a particularly difficult reading. So there's one thing that's, I guess a couple of things that are really important. Okay, we talked about the idea of what arbitrage-free means. Okay, we force that to be the case, right? We calibrate things to be so that they're going to give us arbitrage-free values for the benchmark securities, whatever we're comparing to. When we say benchmark security, in your mind for right now, just say treasuries, right? Okay, we can apply that to pathwise or our Monte Carlo valuation. Okay, but what I think is going to be most important here, okay, is that you understand what's going on with the binomial model and the use of backwards induction within the binomial model, because that's what's going to flow over to other places in the curriculum. And there's actually a lot that we can learn from looking at bonds with embedded options via this binomial model. So make sure you have a handle on that, how to use it, and then understand the principles of what we're talking about otherwise, and I think you're good to go on this little reading.